just saw that. Come on, record. There. Again, on the left, evaluating an expression with an imaginary value. On the right, solving an equation involving an imaginary value. We then took this idea and went into 6-8. And what was the idea of 6-8? How did that differ from 6-7? We didn't just look at imaginary constants. What else did we include in 6-8? Remember it was called the complex numbers? That was the idea of 6-8. We looked at complex numbers in general. So instead of just having an imaginary part, it also had a real part. So for example, something like this. And then multiplying those out. Recognizing that we're going to get an imaginary answer from this. Now, when did our answer become real? What had to happen to get a real answer from two things multiplying as imaginary? The I has to be squared because what do we replace I squared with? Negative 1. Good. So an I squared exists. It becomes real. Now, specifically for binomials, what do the binomials have to be for them to multiply out to give me a real answer? Only real answer. What do they have to be? Give me a general term or an example.
Binomial conjugates.
Yeah. And we'll say complex conjugates, but conjugates, exactly. Conjugates in nature. So if I had this, though, okay, that's the example of complex conjugates, that would yield a real solution because the middle terms cancel out, leaving us with 4 and then negative 9i squared. Okay, again, 4 minus 9i squared. Recognize that I squared is negative 1, so just make this a positive and drop the I squared. And you have 4 plus 9, which is 13. Okay, so this was 6-8. Now, how could that problem be asked? I could say, I could say this, ready? Evaluate that topic of complex conjugates, I could say evaluate the expression 2i over 3 plus 4i. And you can't evaluate this without multiplying by the complex conjugate of the denominator. And thus, almost like rationalization, like you're rationalizing a denominator with a square root in it. There you would multiply by the binomial conjugate. Here you're going to multiply by the complex conjugate. 3 minus 4i over 3 minus 4i. How else could I ask this? I could say the following. And I'm not going to go through every single step because most of you guys are good with the skills. That's what I'm noticing now. Your skills are there. It's understanding when is the question going to be asked and how do I attack it. So I'd rather present you with this question and just give you this instruction. You know what? This is what you're going to have to do, and you can go through the process of actually doing it. The denominator should be real as an answer. The numerator is going to be imaginary there, and that's okay. But we have to recognize that our answer should be written in A plus BI form, complex form. So whatever your answer turns out to be, you write it in A plus BI form. So another way to ask the same question, another way to do it would be this. Saying the following. If g of x equals x over x squared plus 1, then find g of 1 plus 2i. Well, what does that mean? If it was g of 1, you would take the 1 and plug it in for x wherever you see an x. So you take the quantity 1 plus 2i, plug it in these spots here and here. In the denominator, you're going to have to FOIL 1 plus 2i, 1 plus 2i, plus 1. The numerator is just 1 plus 2i. So this is just going to be a lot of work, right? A lot of process. So a problem like this might take you 2-3 minutes if you are skilled in it. It might take you 5-6 minutes if you're not practiced in this area. So make sure to practice this. Plug this in for x squared here. Square the entire quantity. Plug the numerator in. And then go ahead and, in quote, rationalize your denominator, even though you're not really rationalizing it. Okay? You're not really rationalizing. But what would it look like? Okay, I'll put the beginning part through. So we've got 1 plus 2i over 1 plus 2i squared plus 1. So I'm literally plugging it in here and here for those two spots. And then the bottom you have to evaluate first, right? You can't do anything else. Please don't try and multiply by the complex conjugate of the numerator. It's the bottom that we want to make real, not the top. So the bottom has to be FOILed out. Add the 1 to that answer you get. You're going to have an imaginary answer on the bottom, which you then have to multiply by the complex conjugate to get rid of the denominator. Okay, but it's the process that I'm going to go over right now. your mock test and these, problem sets and these examples are where you guys have kind of learned that skill. It's applying the skill, I think, that causes people to make mistakes on tests. Okay, and then what's the other thing I always talk about? Yeah, careless mistakes. Please be careful with your work. Okay, negative signs, it's scary sometimes. Okay, please be careful with your work with that. Not that it's funny, but it's just that there's so many points lost for things that, realistically could be corrected. Okay, and that comes back to what? Pacing yourself. So that's part of the reason that when I'm doing this review right now, I'm thinking today that I'm going to really go through strategies on how to get through the test and how to understand when to apply certain topics. Okay, what kinds of problems to apply them toward. How about a problem like this? How would we approach this? Square root of negative 16 times the square root of negative 9. Chandler.
You have to turn it into 4i multiplied by 3i.
Yeah, remember that. You can't multiply things under the radical if they're both negative. If one of them is negative, you're okay. If they're both positive, you're great. But if they are both considered, or they both have a negative radicand, you have to evaluate them individually. Why? Because look, 12i squared, which is what? Negative 12. Negative 12. Because I squared is negative 1. If we had multiplied 16 times 9, we would have got 144. And then the square root of that, we would have gotten an answer of positive 12, because we would have taken the principal square root. So again, we cannot multiply these numbers first, or else we would get this. It is not correct. That would give us 12, which is clearly different from the actual answer of negative 12. Okay, one of the few exceptions to the rule. Okay, exceptions to the rule. You should definitely be able to solve an equation involving completing the square with imaginary numbers. Recognize that when completing the square is really occurring. So if I give you a problem like this, believe it or not, you're actually completing the square in this problem, but it's already been completed for you. All you have to do is solve. But this is what completing the square kind of leads us to. It leads us to this. It leads us to saying, okay, we're going to have some binomial squared, and that equals some number. Right? I divide by 2, divide by 2. And then as a result, we have to take the square root of both sides. This is where completing the square, the idea of it comes from. The first day we did that, we started by looking at simple examples like this, and we led to the idea that when we have a binomial squared, it's very easy to solve an equation. We take the square root of both sides. We square root both sides. The left-hand side dropping the square. The right-hand side, we take a look at the square root of negative 4. Since it's an equation, we recognize positive and negative solutions. That becomes 2i. And how do I get rid of a negative 4? I add it to the right-hand side. And I'm going to always add it or subtract it right in the front right here. And that's our answer in simplest a plus bi form. In simplest a plus bi form. Okay? You understand that? Now, completing the square itself, let's do one quick example of this. So for this one, we're going to say if we had x squared, and it does not matter. You can pick any numbers for practice when you're at home. Literally, make any equation. It always works completing the square. Always. Let's put a 2 in front. Plus 6x minus 7 equals 0. I'm going to recognize the steps are to move c over first, then divide by a. So it's the steps we have to know. So move c over, divide by a. So we're going to get x squared plus 3x equals 7 halves. I move the 7 over by adding it and then divided everything by 2. I then recognize this might be a little bit difficult because I have a 3 there. But it's really not that bad. What's half of 3? It's just 3 halves. Please don't use decimals. Do not write this note down. Do not use decimals. Fractions are so much easier to square and combine than decimals are. Use fractions. So think of 3 halves, because you want to take half of whatever b is and square it. Square of 3 halves gives you 9/4. It's a lot easier to square. 1.5 squared is 2.25, which is 9/4. But writing this as plus 9/4 on both sides makes it a lot easier on the right-hand side. Okay? Now, obviously, if the decimals are really, really, really simple and they're all 0.5s, it's okay. Do whatever you want. But It just makes it easier on you, I think, to do it this way. Now, what does this always factor into? That's the key here. I'm always going to get x, and then whatever this sign is right here carries down. But what's always left? Right here. Always. Every single time. Always. Half of b. Remember, this is half of b. So what was half of b? Half of 3 is 3 halves. And then on the right-hand side, common denominator, double this. Double this. 14 plus 9 is going to give me 23 fourths. You know what? It's no big deal. The fact that this is not a perfect square on the right-hand side simply means that this original equation was not factorable. Remember, if you take a square root and it's a perfect square, you end up getting a rational answer, which would mean that the original problem could have been factored. The fact that this is not a perfect square means that the original could not have been factored. Okay? Don't forget the plus or minus. You could write it over 2 separately. If I put the radical in the numerator, and then move the 3 halves over. How do I move a positive 3 halves over? What do? How do I write my answer? M? Okay, that's your answer right there. 2 answers. They are, ready? Classify them. They are 2 real, distinct binomial conjugates. And that means our discriminant will be what in this case? If I had this in expanded form, the discriminant must be what for this to be the answer? For you to get roots like this, where it's all real and you have binomial conjugates, what must the discriminant have been? Positive. The discriminant must have been positive, and it must have also been a non-perfect square. Okay? A non-perfect square. Our discriminant, it's obvious, is what? 23. Look at this answer right here. Like, analyze this. This is the same format the answer comes in with the quadratic formula, isn't it? Look, negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. This is literally it right here. So this is the idea. I'm just writing it as separate fractions instead of all over 2 or something like that. But that's the same solution you would get if, instead of doing this problem by completing the square, you had taken a look and just used a, b, and c with the quadratic formula. Okay? So that leads us to the idea of the question. You should know. I'm not going to do an example. Are we all confident in how to run through an example of that? Okay, but you need to know this. Let's look at the discriminant, which is usually the part where people have a little more of a hiccup. Okay, that's our quadratic formula. And obviously, it's whatever the independent variable is. X equals usually, but it could be t equals or k equals or whatever the independent variable is. Now, 3 cases for the discriminant. The discriminant, remember, is this right here. B squared minus 4ac is the discriminant. And if the discriminant is negative, it means that you have a negative under the radical. Alex, what does it mean if there's a negative under the radical? Yeah, it's an imaginary number. It's an imaginary number when the discriminant is negative. So if that's the case, we know that our roots have to be complex conjugates, or our roots are just going to simply be imaginary. Okay, and there's going to be 2 of them. What if the discriminant ends up being 0? What happens to my quadratic formula if the discriminant is 0, Will? Yeah, we have a double root. And they're real. It's 1 root repeated twice. Why is that? Why is that the case? When the discriminant is 0, we get a double root. Who could explain it? You got to be able to understand it, not just be able to do an example. Why is it? Look at the quadratic equation. Why is it that when the discriminant is 0, we get a double root? Sarah?
When you add or subtract 0, you get the same answer.
Take a look. Plug a 0 in that place right there. Negative b plus 0 over 2a. Negative b minus 0 over 2a. Same answer. Plus or minus 0 has no effect on the problem, so you get the same root twice. This would be an example, if you recall, that would be like this. Because this would factor into x plus 2, x plus 2. Get the same root twice, a double root, and they're both real. The third case, when the discriminant is clearly not less than 0, but greater than 0 now. When it's greater than 0, what are the answers? What kind of roots do we get when it's greater than 0? Square root of a positive number. What's the term for it? Inigo, what's the term for this? Do you remember? When you get an answer, right, where you have all values here, here, and this turns out to be a positive number, what kind of roots are you going to get? So imagine your answer is 2 plus radical 7 all over 4. 2 minus radical 7 all over 4. What would you call those? What's the term for them? Remember? Somebody want to help me out? James? Binomial conjugates. Okay? Just like this was called imaginary earlier, I also said you could have called these complex conjugates. And the conjugate part, if you recall, just simply means a plus or minus. In this case, if the discriminant is positive, we'll get something plus or minus something else that's under the radical still all over some number. We call them binomial conjugates. Okay, 2 real binomial conjugates. 2 real binomial conjugates. Those are the 3 cases we have to analyze. Now, how could that problem be A, like I was saying earlier, so I can give you something like this. Oops, let me do it this way. And I could say, determine the value of k such that the roots are imaginary. Such that the roots are imaginary. If the roots are imaginary, the discriminant is what? What's the discriminant? Negative. If the roots are imaginary, the discriminant is negative. So take the discriminant and set it less than 0. That's what negative means. Well, B in this case happens to be what, Jeff? B is k. And then A is 2. That's easy. And what's C? Please be careful. What's C here? What's C going to be, Chandler?
Negative 2k.
It's going to be, yeah, negative 2k, which is really kind of annoying. Because we're going to have to think about that double negative there. And don't forget the 2 in front as well. A lot of students just put the k down because they see that the k is the coefficient. They think of another coefficient there. Don't forget the entire term is the value of C. And then we have to go about solving this. It looks like it's tough, but it's not. It's not, because we're going to be able to take out a greatest common factor. We're going to get k squared. It's going to be plus 4 times 2 is 8 times 2 is 16. 16k less than 0, which is k plus 16 less than 0. See, the GCF is k in this problem here? So no matter what scenario I give you, all you have to do is solve it. But what do you have to use to solve this? It's a quadratic inequality. I need to find the what? Chandler, go ahead. Critical points. So do we see how the earlier stuff in the year comes back? Chapter 4 right there, critical points. So we identify the critical points as the solution as if this were an equation. So the solution, if it were an equation, would be the following. We call these critical points. And we graph them on a number line. And then we simply test the regions. I'm going to test using positive 1. Plug a positive 1 because it's in this region. A 1 here and a 1 here makes it positive, doesn't it? So we put a positive sign. I'm going to test using negative 1. Negative 1 here and a negative 1 here makes it negative 1 times positive 15, which is negative. And then obviously the last region is going to be positive, and I can show you negative 17 means negative 17. Negative 17 plus 16 is negative 1. Negative 17 times negative 1, negative is positive. Well, we want this expression to be less than 0 or negative. That's the central region here. You know what you'll notice? It's always open circle with this. Because when is it closed circle? When you have a double root. When the discriminant actually equals 0, you get the roots of the answer. 0 and negative 16, right? 0 and negative 16 would cause this expression to actually equal 0. That's when you have a double root. That's what you would do. You would set b squared minus 4ac equal to 0. You would have closed circle. You wouldn't even need a number line, right? The answers would just be negative 16 and 0. If I wanted a graph that had real binomial conjugate roots, If I wanted a graph with that, what does the discriminant have to be for that to happen? To have real roots that are binomial conjugates, 2 of them. You need a positive discriminant. So you know what? The region here in blue that I'm shading now would be the region you would shade if you were looking for positive, real, binomial conjugate roots. You would shade this solution out here. So the one in the white in the middle is for imaginary roots. Out here, these 2 regions indicate positive real roots. On the negative 16, on the 0, is when the actual value would be 0. So you would have a double root or a repeated root because the discriminant would be 0 here and here. Okay, so if you wanted to write it, you could write it like this. The discriminant is greater than 0 when k is in this range. The discriminant is less than 0 in that range. And then at 16, the discriminant equals 0. At 0, the discriminant equals 0. It's tough to see this, sorry. Okay, but I'm talking about here. So this, the discriminant is greater than 0 in these regions. And this region is less than 0. And at negative 16 and at 0, the discriminant is exactly 0. And these are the values of k. Remember that this line is all the values k takes on. So when k is 0, the discriminant is 0. When k is negative 16, the discriminant is negative 16. Again, those are the 3 cases for section 7.3. And we talked about functions that are quadratic in nature, but do not necessarily appear that way. Let's look at an example of something that could be a little complicated. Remember the last example we didn't really get to at the end of class? Let's do something like that. So let's say we have this. Give me a second, I have to make sure it works. How about this? Doesn't look like a quadratic that we could solve unless we wanted to expand the beginning, which we could do. We could expand the beginning and it just becomes a little bit messy and it would work. Or I could recognize that this is like a u and I could somehow make 3x plus 1 over here. How could I do that? Anybody know? Anyone look at that last example? What could I break this into? I'll keep the 9x, I'll give you that hint. Keep that 9x.
Put up into 9x plus 3 and 9x, and then plus 2.
Very good, Jeff. Jeff can see that because look, what's the GCF of 9x and 3? What's the GCF? Everybody, what's the GCF of these 2 numbers? 3. When you take it out, aren't you left with 3x plus 1? So Jeff said to himself, you know what? I need to get 3x, which means I need to take a 3 out of 9. If I take a 3 out of 3, it leaves me behind with a 1. So we broke the 5 into 3 and 2. Okay? You know what? How about this? What if this had been a negative 5? No big deal. Watch. This is negative 5. Well, what's 3 plus what number gives me negative 5? What is it? Negative 8. So just put a negative 8 at the end. And you still get back to negative 5, don't you? So now I break it into 3 and negative 8. But in the end, these 2 numbers sum up to negative 5. But I knew that I needed a 3 right here, because if I take a 3 out of 3, I get 1. If I take a 3 out of 9, I get back to that 3. So I take a GCF out of this piece right here, making it the following. And as a result, our let statement is let 3x plus 1 equal u. Because now it's clearly in quadratic form. And as a result, we go ahead and solve the problem. Now, I don't honestly know if this is going to factor. But if it didn't factor, you could use completing the square. You could use the quadratic formula. Does it factor? Is the discriminant a perfect square? Check if the discriminant is a perfect square. You're going to get 9 minus 4 times 2 times negative 8, so it's positive. 4 times 8 is 64, 9 is 64, 73. The discriminant is 73, so as a result, it cannot factor. So we'd have to use the quadratic formula. Do me a favor. Don't actually solve this. Let's make believe. I know it's not true. Okay? This is not true. Let's make believe the answer came out to be u equals 2 and u equals 3/2. Hypothetically, okay? It's not the answer, hypothetically. If that's the case, we have a definition of u at the top. U in our let statement was defined as 3x plus 1. So if these were our answers, they are not. If they were, we could set 3x plus 1, which is what u is equal to, right here. And since u is also equal to 2, we could put a 2 there. And then we could set 3x plus 1, replacing that u with 3x plus, with 3x plus 1 here, and setting that equal to 3 halves. And then to get the solutions to the original equation that was in x, we just solve these. Subtract 1, giving us 1. X is simply 1/3. Subtract 1 is going to be 0.5. 0.5 divided by 3, we're going to have 1/6. And I did that because I think of 0.5 as 1/2. 1/2 divided by 3 is just put a 3 in the denominator, making it 1/6. So those would be our two solutions for this equation if you could rewrite it in quadratic form. Okay, that's the idea here. Now, please, I am testing you on this. So if I write, solve this using u substitution, I want you to solve it using u substitution. So it might take you a minute to sit there and try to figure out, do you have to break up that constant like we broke it up, like Jeff broke up that -8 or -5 or whatever it was that we chose? Or can you solve this by just looking at the problem and seeing what u is right away? Okay, but you should recognize that as well. I'm trying to think. Other things we didn't cover that you have questions about, please ask. Let's kind of review of all the topics. Yeah, Jim.
Which kind of problems can you reject solutions for?
What kind of problems can you reject solutions for?
Like these kinds?
The kind of problems that you really want to check solutions are the ones that involve square roots that are then changed to something else. So those are the ones you want to look to check your answers for. These ones should all work. Yeah, these will definitely work. Okay? Yes, those ones that you have the square roots involved. Hey, also, I should mention this. With the quadratic formula section, we did look at a few word problems. So I'm going to throw, I think, 3 problems and have you choose 2. Okay, so to give you an idea of that. But knowing that to solve these problems, you cannot factor. I'm not going to make them factorable. We already did that in section 4.5 and 4.8 or whatever that was. Okay? So the problems that are word problems, you will not be able to factor. Now, if you want to, you can solve in your calculator. Please take it out real quick. You have 5 minutes, I'll show you. On the word problem, I'll allow you to solve in your calculator. You don't have to use the quadratic formula. If the bell rings while we're doing this, just know that on Moodle I put a document that teaches you how to solve using a video that teaches you how to solve using the calculator. So if you are in doubt, please take a look at that. I just got my computer reformatted. My calculator's not on here. I had a virtual calculator on my computer for a while. All right, I can tell you how to do it. I have it up there. Ready? Go to Y1. Go to Y1. Type in the following function. X squared plus 5x minus 2. Okay, now hit zoom 6, and that will standardize your graph from -10 to +10 on both axes. Do you see 2 roots for that one by any chance? I hope you do. I hope they're on the graph. Are they? Go back. Go to, it'll bring you to the error. So you just have a squared symbol there. You can remember x. So second insert before this, you need to put an x right there. And then you can zoom 6. Okay? So you see that there's 2 x-intercepts. Who does not see 2 x-intercepts? Okay, great. Press second. Then press the button that says trace. It says calc above it. Because you're calculating the zeros of the function. So choose number 2. You can go down and hit enter or just press number 2. And you want the zeros. I think we did this once, but to reiterate it again. You look at one of your roots, the one on the left. The one on the left is between -5 and -6. Do you all see that? Does everybody see a root between -5 and -6? So to the left of the root over here is -6. So press -6 for left bound and hit enter. It's going to say left bound question mark. It says left bound question mark. Press -6, enter. Then right bound, press -5, enter. And then just enter one more time. I said it won't work. What did you do?
Wait, sir.
Did you get an answer? What did you get? M, call yours out.
It says 0x equals -5.3722.
What did others get? -5.3722? That's one of your roots. Now, the answer would have been something like this. Ready? -2 minus radical 7 all over 5. So when you do the quadratic formula, you get the exact answer. What kind of an answer is this? What's the opposite of exact? What is it? An estimate. Remember, when you put a decimal, you're rounding, aren't you? But a radical is exact. It's kind of weird to think about that. 2 plus radical 7 over 5 is exact. But as soon as I estimate radical 5 with the decimal, like you're doing here, you guys see dot, dot, dot on there? Does it show dot, dot, dot? It is dot, dot, dot. It goes on forever. There's a lot of things going on because it's irrational, the answer. Find the other root. The other root looks like it's right around 0. Press second, trace.
Second trace of what number?
After you press second trace, choose number 2, which is 0. And for the left bound, pick a number just to the left of it. So this is like 2 left. So choose like -1. And then choose like +2. So right back. Pick a number to the right. See those arrows you pick up? Searching the window means. So once you search in the calculator between those arrows. Hit enter and it says yes. Hit enter one more time. That's one of your answers. Right? See what time it is? See? And 3.
Yeah.
Specific word problems do not.
If not, you're back to school. I mean, we have the ceremony today for school, which I should really be at, unfortunately.
I have to take